Hello everyone. In the previous lecture, we were discussing some preliminary concepts uh, in this energy methods chapter, and today we'll be moving on to another very important concept which pervades through uh, all of our discussions, all our later discussions, and that is the concept of virtual displacement. So this definition of virtual displacement that I have pointed out here, which I've written out here, is actually a quotation from a very famous book called Classical Mechanics by Goldstein, Poole, and Safko, which is quite popular among physics undergraduate students. We are not going to use anything else from that book, but if you are interested, you may take a look. But this particular definition of virtual displacement is given in a very nice fashion, so I took it from there. All right. So what it says here is that a virtual infinitesimal displacement. Okay, so please note that although I've mentioned it to be virtual displacement here, what we had what that book discusses is really the virtual infinitesimal displacement, and we'll see in a more concrete fashion what's the difference between these two. Okay, so a virtual infinitesimal displacement of a system, it refers to a change in the configuration of the system as a result of any arbitrary infinitesimal change of the coordinates. But when we are doing this change, we have to be very much consistent with the forces that are imposed on the system as well as the constraints that are imposed on the system. So this is very important, that we respect the forces and the constraints. So a little discussion about respecting the constraints as far as uh, our discussions of admissible paths was concerned, we have already had in our previous lecture. So again, we encountered this important thing, that we have to respect the forces and constraints. All right. Uh, Now, uh, what is the difference between this virtual displacement and a real displacement? So that part is mentioned here. So this displacement is called virtual to distinguish it from an actual displacement of the system which occurs in a time interval dt, during which the forces and constraints may be changing. So when we are talking about an actual displacement, okay, so when we are talking about an actual displacement, we do allow for the forces and constraints to be changing in a little interval dt. But when we are considering a virtual displacement, we are talking about a particular instant t, the time t, at which the forces and constraints um, do not change. Okay, so written in this fashion, it seems like quite a complicated thing. Okay, uh, so it is true that there are certain subtleties involved, and let's see if we can break down these things in a step-by-step fashion to understand how really a virtual displacement can be actually realized. Okay, how can we bring about, or how can we actually think of such a virtual displacement in a step-by-step fashion? So the first step towards that is that because we are indeed talking about the changes in the coordinates of the system at a given instant time, at a given instant of time t. So the first thing that we do when we want to realize a virtual displacement is to freeze time. Okay, we freeze time, and this is the part where you really go into that virtual domain. Okay, so if you're tracking the evolution of a system as time progresses, you are actually looking at the actual displacement, the actual changes in configuration of the system. But the moment you freeze time and yet allow the configurations to change, you are in the virtual domain. This is the most important thing to note. Okay, so once you have frozen time, you consider paths in the configuration space. Okay, so consider paths in configuration space corresponding to some variable t dash. which, mind you, is strictly not time. Okay, so this t dash is just some arbitrary scalar variable, and it is anything but time, because we would be varying t dash, but note that we have already frozen time. So because t dash is varying and t is frozen, the time is frozen, so t dash is certainly not time. Okay, this is very important again. All right, and then we restrict to paths which are admissible. That is, we must respect the constraints of the system. Okay, we restrict to paths which are admissible. Restrict to admissible paths. So you see now why we had to make such a big deal about defining those preliminary concepts in such a clear-cut fashion in the previous lecture. Okay, so each of these things, the admissible, path, all of these things have a very specific, well-defined meaning. So I urge you that if you have not seen the previous lecture, you please go through it in proper detail. All right. So now that we know how to realize this thing, this virtual displacement, can we take a more concrete example to perhaps see what is really going on? And in order to understand this in a concrete fashion, I think it's best to consider the simplest of mechanical systems, which is a single particle traveling along a certain direction. Let's say that it is moving along the x direction, and let's see what happens to it. Okay, so let me go to the next slide here. Okay. So what I'll do is, um, okay, so let's say our particle is moving along the x direction, and it is moving along the x direction. Uh, so it is occupying different positions x uh, as time progresses. So what we'll do is, we'll say that let this be the time axis, and let this be the x axis. Okay, so since x is a function of time, that is why we put x along this uh, vertical axis, and t is along this. So please note that this t is very much time. Okay, this is not the t dash. We'll come to the t dash part. So this particle is moving here. So let us depict it like this, something like this. Okay, so as time progresses, so for corresponding to each time, it has a certain x. Okay, so different points in time, it has a certain x. No big deal, you are all familiar with this. Now we wish to talk about the virtual displacement. So first step, as we had discussed in the previous page, was to freeze time. So we do that. Okay, so we freeze time. So suppose we consider this t is equal to t naught. At this t equal to t naught, we freeze time. So at that moment, this has a certain value. Okay, this has a certain value. So that is the value x at t is equal to t naught. Now you see, we want to explore the changes in x respecting whatever the constraints may be on the system that are present at that time t is equal to t naught. Okay, because we have frozen time, so whatever constraints were present, even if those constraints were time changing, but whatever the situation with the constraints was at time t equal to t naught, we have to respect those constraints, and respecting those constraints we can explore the variations in x. But now, looking at this diagram, how can we change x? Okay, we want to keep on changing x corresponding to some real variable t dash. So I mean, we are running short of directions now, because you can't move along this direction, because that would be unfreezing time again. But we have to keep time frozen, so we have to remain on this thing. Okay, we have to remain on this thing, and we have to keep on changing x. Now, please don't think that, I mean, Of course, in a certain sense, what you can say is that this particle can move like that, but uh, what is the other variable? What is the independent variable that is changing here? So in this particular way of looking at the axis, it is not possible to depict it. So we have to go to a three-dimensional version of this. Let's see if we can do that. So what we'll do is we'll take our time axis like this. This is our time axis, and let this be the x-axis. Okay. Now things will become clearer. And now you think of uh, another axis. Okay, think of another axis like this. So what is this axis? So this is our t dash axis. So this is t, this is x, this is our t dash. Now you see, and let us, of course, on this tx plane, let us depict for once the actual path that we were considering. It was something like this. So this is basically uh, this thing is just drawn here. Okay, I hope it is clear. So, and what we had done here is basically to take this point t is equal to t naught, and we had considered this point here. Okay, and now we want to explore the variations in x. How can we do that? Well, what we'll do is we'll vary this t dash, and we'll consider the variations in x corresponding to such variations in t dash. So basically what we are going to do is we are going to make or plot out the changes in x uh, in a plane which is parallel to this t dash x plane. I repeat, we are going to depict the path of this x of this particle. Path means tracking out the various configurations or positions of this particle, or changes in x. All of these are equivalent things to say, corresponding to changes in t dash. Okay, so uh, let's say that we, and please note that we are starting out from this point, and this point is what? This point corresponds to t dash is equal to 0. Okay, so let's start out from this and maybe track out a path like this. I repeat, this point here, it depicts t dash equal to 0. Okay, and then t dash may be increasing, corresponding to which x is also changing values. Okay, so and this curve that I have drawn here, this path that I have drawn here, it is in a plane which is parallel to the t dash x plane. It is very important to note that when we are changing this x here, we are not at all deviating from this t equal to t naught. Okay, so if you can imagine a plane here. Okay, if you can imagine such a plane, maybe I can draw it here. Okay, so that plane, on that plane, this t equal to t naught is a constant, which is how we are respecting the first step, that time is frozen. Okay, but that does not mean that t dash cannot change. T dash is very much varying, x is changing along with it. So this blue path that we see here, that is a virtual displacement. Okay, so any change in configuration from here to here. Okay, from here to here. So as we go along that those will be virtual displacements. So we have to consider now the concept of virtual infinitesimal displacement. All right. You also please note that that x corresponding to t that is the time equal to t naught, is very much equal to x corresponding to t dash equal to 0. Okay, if you understand this, a lot of the things you will understand. Okay, so let us consider the virtual displacement of the particle at any time t dash. Okay, so virtual displacement of the particle at any t dash. So let us depict that virtual displacement by u. So x t dash minus x t dash equal to 0. Okay, so after this point I will just write x corresponding to 0. Now this thing, it can be Taylor expanded about 0. Okay, so as I mentioned, whenever I'm writing x of 0, I basically mean x at t dash equal to 0, which of course is equal to x at t equal to t naught. Okay, so I'm not repeating in every step that's those statements. So in the next step, I'm going to Taylor expand this. So x of 0 plus t dash. I can write this as minus 0. Of course, all right, let me write that. So that divided by factorial 1, which is just 1, then dx dt dash with evaluated at t dash equal to 0 plus half t dash minus 0 square dx square dt dash square evaluated at t dash equal to 0 plus higher order terms and then minus x of 0, which was also present here in the previous step. So you see this x of 0 cancels with that x of 0. So ultimately what we are left with is this term here and this term here. And we can write this using the delta operator in the language of calculus of variations. Okay, so you think about it for a second, it'll make sense. Okay, I'm not asking you to make formal mathematical sense out of it, but just try to make sense of it by drawing some analogies with our previous discussions, especially with what we were talking about in our previous lecture, or rather in our first lecture. Uh, uh, Sorry, the first chapter on calculus of variations. So you see this delta u, this is the first variation of, uh, of u, this is the second variation of u, and uh, we have to use this kind of a depiction. Okay, it makes sense here because of course I have to write this higher order terms here. I'm not writing explicitly. So this kind of a depiction, it makes sense here because you note that the original independent variable of our problem, what is the original independent variable of our problem? It is the time t that we have frozen in time. Okay, that we have frozen, that we are not changing. So we are exploring changes in the position of the particle without changing the independent variable, and that is exactly what this kind of the delta operator it denotes. Okay, so you go back to our discussions in our calculus of variations where we made a strict distinction between dy and delta y. Okay, so dy is always accompanied by changes in the independent variable, which is dx, but delta y is changes in y keeping the x the independent variable constant. In those discussions, our independent variable was x. Here, the independent variable is t. The actual independent variable is t, and it is x which is actually corresponding to what was y in those discussions. Okay, so you understand that why. I hope you all understand why this delta operator, the variational operator, it makes sense here. Okay, now very importantly, you note that uh, when our t dash is indeed very small. Okay, so when t dash is very small, this entire u, that is more or less uh, properly captured by this delta u. Of course, a little bit of difference will be there because we are not considering these higher order terms, but u will be approximated, well approximated by this delta u, provided our t dash is very small. So this basically what we are saying is that t dash minus 0 is very small. So u is well approximated. In such a situation, u is well approximated by only the first term, which is delta u. And it is this delta u which you can think of as the virtual infinitesimal displacement, which we're talking about in our definition. Okay. All right. I know even from my own experience that usually when we talk about virtual displacements in terms like in hand waving terms, that is often done in our undergraduate classes. So it always leaves some sort of doubt or confusion in our mind that what really is the difference with the actual displacements. So with this discussion, I hope that difference uh, is somewhat clarified. Okay, the primary difference is that we are indeed freezing time. If you understand that, you will automatically understand that at that frozen instant of time, all the forces and constraints, even if actually they are changing with time, but once you have frozen that, that is not changing, and then you explore the changes in the configurations of your mechanical system respecting those particular forces and constraints as they are at that frozen instant of time. And then moving on further, if you consider a little infinitesimal displacement by keeping the time constant, then what you end up with is the virtual infinitesimal displacement, which is all important in the rest of our discussions. All right, with that, I'll end this lecture. Thank you very much.